what's your view about that? Because I find linearity a rather artificial kind of concept.
That was one of the reasons I moved to biology, because the emergence of order and pattern there is fundamentally non-linear. And I would, as a hunch, say I would expect non-linearity to come in to...
But so you're just doing it because, well, what else can we do? Is that...
I'm presenting a toy model
right.
at this stage, because as I say, we don't have any... I mean, we're all groping in the dark if we try to say, I know what the mathematical description of process should be.
Also, makes drawing a distinction between the things on the left and the things on the right. He's not saying it's all...
The left is
This was my potted description of quantum theory, really.
Right.
I should have had quantum mechanics here when I said mechanism. Sorry. I was actually... I'm actually trying to put up what we're doing in quantum theory, or in quantum mechanics, contrasting what we would do in a process view of the same thing. So sorry, I was unclear. I'm kind of...
in defense of linearity, I don't think linearity is that trivial if you have it in many different dimensions. There are these mean, there's theoretical...
No, I'm not saying it's trivial. I'm saying it's trivial. I just find it slightly artificial.
It's very restrictive.
I'm not sure. I mean, you have these mean field theories which put something in a non-linear approximation from what's basically something linear.
Something, if linearity emerges from a non-linear structure, then that's of course something profound. But as a
non-linearity,
linear way around. Anyway, let's.
I have a suggestion, which is that we're going in so many different directions. This discussion at the moment. The great thing would be to let Nick get on to his toy model and specifically how it connects with the Weyl algebra. We might then have a better handle on what he thinks is the way to go.
Right, so Basil's, I agree. So Basil's already, I think, described this morning, the idea that we can have a purely algebraic representation of quantum theory as we know it, and Basil did this in much more detail than I want to. And that basically we're representing state vectors, which we normally put in Hilbert spaces, as elements of minimal lateral ideals in an algebra. So now we have a single algebra, the operator algebra, in which we distinguish these subspaces, linear subspaces, which contain the state vectors. And it needs to be linear subspaces so we can have linear superposition to actually do quantum theory. And we generate the dynamics through inner automorphisms. So A is an element in the algebra, alpha is another invertible element in the algebra, and this will actually encode our dynamics. And Basil showed in great detail how we go from this picture to getting out all the conventional Schrödinger equation and various other equations. And Basil was looking at the bosonic case, but could also have done the fermionic case as well. Okay, so...
You write E instead of delta now, okay.
I write E because...
That's the paper we wrote together.
Yeah. I've always called it E, but I'm not sure. I think your delta is the...
It's probably a...
It's related to E, but it's not exactly the same as E. Anyway, because did you have your delta the other way around? I think you had x delta as 0.
Yes.
And delta P
yes.
0.
Okay.
So this is the other one. This is the other idempotent. So we connected. So Basil showed the extension of the Heisenberg algebra with the idempotent delta this morning. You can also do it with an idempotent E in this way, where P is 0 and EH is 0, because are related but slightly distinct primitive idempotent.
This is not the delta function.
This is not the delta function, no.
Or the analog of, let's be careful, the analog of.
Right.
This is not the
But
it's the Fourier transform of the...
It runs along the same lines, but the E I'm going to show you that's in the Weyl algebra satisfies these properties. And so we've Basil's done this for me, so here's the Weyl algebra again.
No, I didn't do the discrete one, you emphasised...
No, you didn't do it, okay, you didn't do the discrete one. I meant you've done inner automorphisms and metastructure groups and all that. That's all been done, I'm glad to say. Okay, so we have the Weyl algebra, and it's well known that it goes to the Heisenberg algebra as n goes to infinity, so it's a discrete algebra, n squared elements in there, or size n squared, and what it actually goes to as n goes to infinity is the extended Heisenberg algebra. So the Weyl algebra, unlike the Heisenberg algebra, is not nilpotent. It has within it primitive idempotence, and so it has minimal lateral ideals in there. And so I just want to show how we can, what we really want to do, as we've said, is have some mathematical representation of process from which we can abstract a notion of space-time. That's our ultimate objective. And what that notion of space-time will be and what the mathematical representation of the process will be, we don't know for sure, and we're not going to work it out today. What I want to show here is how, in this case, we can get out of the Weyl algebra something that starts to give us a notion of a phase space structure, in the case of the Weyl algebra, just to show how we start to get the notions of a phase space order out of the algebra, which we're using to represent a process, if you like, or you may not like. But this is the toy model. So this is our algebraic representation of process, and we're going to start to extract things from it. Okay, so a basis for the Weyl algebra is given by these elements epsilon, alpha, beta, which are just polynomial superpositions of the U's and products of the U's and V's, the generators of the Weyl algebra. And they satisfy this orthonormality rule that the product of two of your basis elements of the algebra is 0 unless beta equals to mu, and is unit magnitude. Okay, so the Weyl algebra, or the Clifford and the symplectic algebras, when we go to the continuous case, actually encode within them both the dynamical laws of quantum mechanics explicitly, but also the geometry of the space on which the quantum mechanics is occurring. So it's only space in this case, or phase space, not space-time for a start. And the Clifford algebra encodes the rotational properties of the space, and the symplectic algebra the translational properties of the space. So what we can do in the Weyl algebra is just look at this very simple structure to see where the phase space is coming in and what the locality properties are under inner automorphism, the restructuring of the process. So I want to show that it naturally has a space in it in which the locality is not preserved under the process. That's the important feature that I think comes out of here. So we can actually order those primitive idempotents. So the epsilon alpha betas were the basis. If alpha equal to beta, so epsilon alpha alpha is a primitive idempotence. If I just quickly go back to the defining relation, if we have epsilon alpha alpha, then you can see that if you... Sorry.
No.
Alpha alpha times itself just gives you back alpha alpha. So all of those are primitive idempotents, the epsilon alpha alphas. We can introduce an ordering operator within the algebra, which I'm calling suggestively x here. Delta x is just some real number, which in some way is giving me an idea of actual physical space that comes out in the end. And so this combination of primitive idempotents is itself an ordering operator on here, in that if I operate on each primitive idempotent, it gives me, in some sense, position in space. It orders them. There's a second set of primitive idempotents defined with prime now, and we can define a second ordering operator on this set of idempotents, which works in just the same way, that it just essentially gives us position along the line. The U and V, the generators of the algebra, in this with those definitions of x and p, just become translation operators because they satisfy these relations. And so if you then operate on so if I define now, in again a suggestive notation, this particular set of my basis elements, these are actually the elements of a minimal lateral ideal now, a minimal left ideal,